So let's move on to the first bit of basics here, strings. This took me a while to get straight, so I'm glad to talk about it and explain it. I came from the old days using C and Python 2, and in C and Python 2, they both did something that in retrospect was a pretty bad idea. They made 1 byte equal to 1 character. And so an array of bytes was exactly the same thing as a list of characters. And that seemed like a great idea when we were only thinking about English. But in the modern world, you have Japanese and Arabic and everything, and a lot more characters than can fit in 1 byte. And that means you have to get over this idea of thinking of a character as equal to 1 byte. And I didn't realize how deeply I had been hypnotized into that until I tried to use Python 3, and I couldn't understand it for a while. So the strings, which are really important, are completely different than byte arrays. So let's take a look at this greet code. If I nano greet.py and make it a little bit bigger, I think. There. All right. So this is how you process strings, which is very much like the way you did it in Python 2. You can just, by the way, Python 2 is a loosely typed language. You don't need to define what the variables are. You can just give it a name and set it equal to something, and it will guess what you mean. So since you put something in quotes, that must be a string. So this makes a string holding that many characters, about 12 characters, maybe 13. And then I can print it out, and you can refer to portions of a string. You can go starting at 0 and up to but not including character number 3, or any other number 3 to 6, or you can go this way with a negative number, ending at the end, and that'll take counting from the end. So this will show you various subsections of a string. You can also use a string as an object. Everything in Python is really an object, and it has attributes and methods. You don't need to know that to do simple things, but it is true that everything is an object. So the greet object has a find method, and you can do greet.find to find a string here, and when it finds it, it will return the numerical location of that. So there is a comma in this string, and this will return the location where the comma is. So I can now print out the portion before the comma by going from the start up to that location. These are useful tricks. As we go on, you're going to have to do some string processing, and those tricks are worth knowing how to do. So I can run that one with Python 3 greet. All right. And so here's hello world. Here's the first 3 characters. Here's the next 3 characters. Here's the 3 characters at the end. And here's the part before the comma. Hello, not including the comma. So that's simple enough stuff. A useful trick. And now we can talk about how those Pythons are actually stored inside the system, which is very different than earlier programs have done it. But before that, let me get a little bit of networking here. Let's take a look at this one. Echo. All right. This is how you do networking. You import the socket library. Now, the requests library we used before does HTTP requests, and that's fine if you just want to fetch web pages from web servers. But if you want to do generalized networking on other ports, like port scans and such, then you need raw sockets. And these are the standard Berkeley raw sockets. BSD sockets have been around forever that created the networking that led to the internet. So when you import the socket library, you can now create a socket object with the socket method. So s equals socket socket. We'll call the socket method and create a socket object called s. Now you can use the s object and perform methods to do things. This will connect to one of my servers on this port 10201. This will now print whatever is received in response to the connection. Now the connection performs a TCP handshake, SYN, SYNAC, ACK. And if the server has a response, including a prompt, it will get it right away and print it here. Then I'm going to send this data, hello from Python and a carriage return with the \n. In order to send data in Python 3, you must send a byte string. And as I've said before, a list of characters like this, a string, is not equal to a byte array, and not anymore. To convert this into a byte array, you have to give it the encode method. and that's what makes it so it can be sent in Python 3. And so it'll send that string, and then it'll print whatever the server says coming back to me with the receive method, and then it will close the socket. So that's what that command, that's what that script does, and that is echo. So I can do Python 3 echo. All right. And so it says, hello, what have you to say? That's what my server says for a prompt. And then when you send it anything, it will just repeat it back to you. You said hello from Python. So it's not super exciting, but the point is it shows that I'm able to connect to a server on a port, and I'm able to send data to the server, and I'm able to receive data from the server. So now I can do, in principle, anything. So now you got a few challenges. Connect to this thing and send goodbye instead of hello, and you'll see a flag. Then go to this one where it sends you a number, and you have to add 1 to that number. So you're going to have to take the data that comes back, put it in a string variable, pick the number out of it, and then figure out how to convert a string into a number. And on you go. Now we're getting up towards doing stuff like brute force attacks, where we'll try a list of names and passwords until we break into a server. So for that, we're going to need loops. So let's take a look at how loops work in Python. This can be loop. I might already have that here. Looks like I do. All right. So there's 2 kinds of loops we're going to use. One is numerical loops. So for I in range of 3, this will go 0, 1, 2. Just giving you a counting up numbers. So that's one way. The other way to do it is characters in a string. So this C is a character, and you can just say in a string, and it will go through those one by one. So if I run this one, Python 3, loop, you see it's 0, 1, 2 for this part, range of 3. And for this one, where I'm going through the characters in cat, it's just CAT. So that's how you loop through characters and how you loop through numbers. And there are other things you might want to loop through, like words in a word list, but that'll do for the moment. And so now you've got some more challenges. Connect to a server. It'll give you 2 numbers, and sometimes they're short. And you have to find those numbers and add them together. But sometimes you add them, and sometimes you subtract them. This one is subtract, 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 then add. So you're going to have to read this string and figure out whether it wants you to subtract or add, then find the numbers, then perform that, and do it. So you have to get 5 answers correct within 5 seconds, and that's to prevent somebody just doing it by hand. You're not likely to be able to do it that fast by hand. You're going to have to automate it. So that's some challenges. And there's the part I was talking about before that I found most interesting, is ASCII encoding, because from doing buffer overflows with C and all sorts of other programming, I was very, very, very hypnotized into believing that a string is just a list of bytes, and every byte is 1 character. And here's where we get to see how much that is not true. Now in Python 2, that is true. You can set a variable equal to \x is the way you put in hexadecimal codes to store just a byte. And I can put a byte in a string object in Python 2. So I have the hexadecimal 41, which is a capital A, 42, which is a capital B, and FF, which is not a valid ASCII code. It's an unprintable character. And if I look at that, it will print it as the string AB and then binary FF, which is how it represents something that is unprintable in Python 2. And if you look at the first element, A0, it's an A, the next element's a B, and the next element is the byte FF, which is a byte value, even though it's not a printable ASCII code. And I was very used to this kind of stuff, but that is absolutely not what happens when you try to do that in Python 3. So if I bring up Python 3, and I put in that stuff, even at the beginning, when I define it with what I think are 3 bytes, I get A, B, and then I get a strange character here, a Y with an umlaut. Instead of seeing a raw hexadecimal value of FF, something weird has happened to the last character. So if I look at them one by one, A of 0 is here, A of 1 is here, and A of 2 is that strange character, which means it's pretty weird. I don't understand what's going on. So if I want to see the bytes used to store the string, I use the encode method to turn the string, A is a string object, and I want to turn it back into a byte object. So I do that with A encode. And now I see the first byte is 41 and the second byte is 42, which is what I expected, but the third byte is C3, even though I set it to FF. And there is a fourth byte of BF. So when you set a string to the hexadecimal value FF, it turns it into 2 bytes C3BF, which I found baffling at first. And then I realized I have to learn Unicode. And this is, in fact, very, very brilliant. This is Unicode, and I was very pleased to see that this is familiar territory to me. This is just like IP version 4. You need the ability to encode a lot of characters. Not even just 65,000, but all the characters and all the languages you want to include in your computer. So they did it this way. If the first bit is 0, the first 128 possible values are the old-fashioned ASCII. Those you store with 1 byte. If the first 2 bits are both 1, then you have this group. If the first 3 bits are 1, you have this group using 3 bytes. If the first 4 bits are 1, you use 4 bytes. So this is very reminiscent of IP version 4 with classes A, B, C, and D addresses. And what it means is your Unicode characters can be up to 4 bytes long, and there are 2 million of them. And they call those Unicode code points. So you can encode up to 2 million characters, and that's enough to encode all the Chinese and Japanese and Arabic and everything else and Russian, everything you want to encode, and that's the point. So now, to make a Unicode, you use \u instead of \x, but the first dirty trick is you must include all 4 bytes here. So if I try to do these various Unicode objects, the first one fails. In fact, that's because the first one's missing. Let me just try this again. Clear a little bit. I skipped a character in my copy and paste. The first one is supposed to work because the first one is the same thing we did before. All right. So the first one is just \x41 interpreted as a string, and that is a capital A. If I try to do that with Unicode, I'll just get an error. And it reminds you here that the correct way to do it is you have to have 4 bytes, which is 8 characters of hex. So I can't have just a 41, I can't have just a 0041, and I can't have just 4 zeros and 41. The only thing that's legal is a \u, 6 zeros and 41. And now I've found another way to express A in Unicode. Because, of course, for the first 127 or 128 characters, I'm not quite sure about 0, they're identical to ASCII for backward compatibility. So now if I take that string and encode it, it will give me the single byte A, 41. And if I encode the Unicode version of it, I still have the same thing, because it's only 1 byte long for the first 127 characters. All right. So that's the game. So now I can try it with FF to understand what happened with that FF. Remember, that's what confused me. When I tried to set a string to hold the character with a hexadecimal byte FF, I got a weird answer. So here, if I define a string with FF, I get that Y with an umlaut, whatever that is. If I try to do it with Unicode, it complains and complains and complains until I make it long enough, 8 hexadecimal characters, and now I've again created that Y with an umlaut. So if I encode it, now I can see I have defined a code point, FF, and that code point is this character C3BF, which is that international character. So 1 byte in a Unicode code point, the code point with this number refers to this character, which takes 2 bytes to encode. And so you got some more challenges down here where you have to find some characters, find the Greek letter sigma, and find the hamburger, because there's all emoticons and all kinds of symbols in the Unicode space, and you can just use them like any other character in a modern language like Python 3 or Rust for that matter. All right.